Hello, welcome to lesson 8. In this lesson, we are going to look at a calculation example, and then we shall look at the combined focal length of two lenses in contact, and then last we shall look at the full formula for a thin lens. Let's look at this calculation example. A convex lens L, a plane mirror M, and a screen S is arranged as shown below, so that a sharp image of an illuminated object O is formed on the screen S. So this setup, when a plane mirror is replaced by a convex mirror, the lens has to be moved 25 centimeters towards the mirror so as to obtain a sharp focused image on the screen. Illustrate the two situations by sketch ray diagrams and then calculate the focal length of the convex lens, of the convex mirror. Let's look at the solution. First of all, they want us to sketch the two situations. This is the first situation, and then the second situation when we have replaced the plane mirror with the convex mirror. So in this first case, we need to know that a ray from the object, or we can consider two rays from the object, goes to the lens and then it is converged to the plane mirror. But since we want the image, since I've said that the image is formed on the screen and the screen is at the same position as the object, it implies that the rays are going to be reflected along the same path, so that the final image is formed at the screen at O. So we shall have our setup like that. So when you look at this, the distance from the object up to the lens is 15 centimeters, and the distance from the lens up to the mirror is 29 centimeters. From the theory, we need to recall that when the parallel rays of light meet the lens, or if the rays from infinity meets the lens, they are always converged to the principal focus. So it means that this position O will be the principal focus, or this position of the screen is going to be the principal focus of this lens. So it implies that this 15 is going to be the focal length of that lens. Then we shall also replace this plane mirror with a convex mirror, and in that case they say that the image is formed still on the screen, but the lens has to be moved 25 centimeters towards the mirror. So it implies that the distance between the object and the lens is going to increase by 25 and it will become 40, and the distance of the lens and the mirror is going to reduce by 25 and it will become 29 minus 25, which is 4. So we shall have this setup. Remember, the image is still formed where at the screen where the object is, so it implies that the rays must be reflecting back along the same path so that the final image is formed here. So when we look at the first case, the action of the first lens, there's going to be a conversion, then it will meet the mirror surface, and then it will be reflected along the same path in order for the image to be formed at this point. So this is how the setup is going to be looking like. Now they want us to calculate the focal length of the convex mirror, the focal length of this convex mirror. So from this ray diagram, we need to note that for this ray to reflect along the same path, it implies that this ray must be coming from the center of curvature of this lens. So it implies that the distance from P to I1 is going to be R, that's the radius of curvature. But we know that the radius of curvature is twice the focal length. So it implies that if we want to get the focal length, we need to get the distance R. But we know that if this is 40, and we know that the F here, that is the focal length of this lens, is 15, we can get the V, that is the position, the distance from L up to I1, using the formula 1 over F is equal to 1 over U plus 1 over V. So we shall make V the subject and shall get that V as a 24 centimeters. So the distance from the lens up to the intermediate image here is going to be 24 centimeters. But remember, this is 4, so this is going to be 20. So r is going to be 24 minus 4, which is 20 centimeters. And we know that r is equal to 2f, so it implies that our 2f is 20 centimeters, and therefore if we divide through by 2, f is going to be 10 centimeters. But remember, this is a convex lens. Its radius, so its center of curvature is virtual. So it implies that f is going to be negative 10 centimeters. Let's look at the combined focal length of two lenses in contact. So here we're going to consider two convex lenses, L1 and L2, in contact. A ray from the object, a point object, goes to the lens and is going to the first lens, and the image will be formed at I prime. But with the presence of the second lens, there's going to be a further refraction, and the final image is going to be formed at I. So if you are considering the first lens, L1, in the absence of the second lens, then the V is going to be V prime. Its image distance is going to be V prime. The distance between I prime and L1 is going to be V prime. And therefore, if we use the lens formula, we shall have 1 over U, so the 1 over F1 is equal to 1 over U plus 1 over V prime. That is in the absence of L2. Now, when we consider the second lens, for the second lens, this first image formed by the first lens becomes the object for the second lens, and it's going to be a virtual object because this ray will not actually be going here, it will just appear to be going here. So that will become a virtual object, and therefore the U is going to be negative V prime, and then the final image is the V, which is distance. That's the distance from the final image up to the lens. So if you're considering the second lens, we're going to have 1 over F2 is equal to 1 over negative V prime plus 1 over V. That's the second equation. When you add the two equations, we shall have 1 over F1 plus 1 over F2 is equal to 1 over U plus 1 over V prime minus 1 over V prime plus 1 over V. This cancels with that, and then we shall have 1 over F1 plus 1 over F2 is equal to 1 over U plus 1 over V. But 1 over U plus 1 over V is equal to 1 over F, which implies that 1 over F is equal to 1 over F1 plus 1 over F2, where F is the combined focal length of this lens combination. So this equation is very important for us. We shall be using in the examples. We need to make a note here that this formula here works for any two lenses in contact. It can be a converging lens and a converging lens, or a converging lens with a diverging lens, or a diverging lens with another diverging lens. As long as we have two lenses in contact, we can use this formula. Then also, whenever we are using this formula, we must consider the sign convention. That is, F for a diverging lens is negative, and F for a converging lens is positive. Let's look at this example here. Suppose a converging lens of focal length 8 centimeters is placed in contact with a diverging lens of focal length 12 centimeters. So it means that our F1 is going to be positive 8 and our F2 is going to be negative 12 because this is the diverging lens. And so using that formula that we have derived, 1 over F is equal to 1 over F1 plus 1 over F2, we can get F, make F the subject, and then we shall get our F as 24 centimeters. And it is positive, so the positive sign here implies that this combined lens is going to act as a convex lens or a converging lens. Let's look at the full formula for a thin lens. So here we're going to consider a parallel ray of light, a ray parallel to the principal axis, a parallel ray to the principal axis at a height h from the principal axis, meeting the lens. So we shall have it this way. So we know that ray parallel to the principal axis is always going to be refracted through the principal focus. Then this is going to be the deviation, and this is also going to be d, since they are alternating. These two angles are alternating, and this is h. Then in the second case, we're going to consider a ray from the center of curvature, and then meeting the lens and then being refracted to the center of curvature, the second center of curvature. Remember, for a convex lens or for lenses, there are two centers of curvature. So you have C1 and C2. So C1 and C2, those are the centers of curvature of that lens. Now, considering the first figure, this is a thin lens. Remember, this is a thin lens, and we want to consider, so since this distance is a small distance, a small height h, we know that d is approximately equal to tan of d, which is equal to h over f, And when we consider the second figure, alpha plus beta is equal to a. Two interior angles added up to one opposite exterior angle. So a is going to be alpha plus beta, and from the diagram still, alpha is approximately equal to tan of alpha, which is h over r1, and beta is approximately equal to tan of beta, which is h over r2. So we shall have that as our alpha and beta. Then we shall substitute for alpha and beta in this equation here. A is equal to alpha plus beta. So we shall have our A being equal to h over r1 plus h over r2. That is going to be the second equation. This will be our first equation. So let us have that one this side. Now we are going to recall that we are considering a thin lens. And we said a thin lens is like a combination of very many small angled prisms put together. So it implies that that deviation d is going to be given as n minus 1 times a, where d, we have it as h over f, and then our a is given by this. So when you substitute for this equation 1, equation 2, we shall be having h over f is equal to n minus 1 into brackets h over r1 plus h over r2. Dividing through by h, we shall have 1 over f is equal to n minus 1 into 1 over r1 plus 1 over r2. This is when we are moving from a vacuum or from air to that lens, when the surrounding medium is air. But if in case the surrounding medium is not air, we need to note that if the surrounding medium is not air, and so maybe is a media of refractive index n1, and the media is of refractive index n2, then the focal length of that lens is going to be given by f is equal to n2 over n1 minus 1 into brackets 1 over r1 plus 1 over r2, where n2 is the refractive index of the material of the lens, and n1 is the refractive index of the surrounding media, medium. Thank you for your attention. We'll meet in the next lesson.